Hello everyone, and welcome back to the Kohi game engine series. Today we're going to go ahead and get started setting up our memory subsystem, and we're going to get started on that right now. Really quick though, I would like to take a quick second and thank the partners of the channel, Eearslya and Wensheng. The partner is the highest tier of supporter on the channel. And so I just wanted to say thank you to our partners as well as our other supporters that are listed here on the screen. So if you're interested in supporting the channel, there are a couple ways to do that now. First off, I have channel memberships available. You can access that by clicking the join button below this video. I'll also provide a link to a video that I have describing the memberships. And I also have a newly launched Patreon page, which is patreon.com/Travis Vroman. And I've set that up because I've had a few requests for that versus the YouTube memberships. So if it's easier for you to use that instead, that is now available for you. So thank you all very much for your support. It is greatly appreciated, and I will be rolling a lot of that back into this channel. So with all that out of the way, let's go ahead and jump into our discussion. As I mentioned before, we are going to be creating at least the start of a memory subsystem. Now you might be asking, what is a memory subsystem and why do we need it? Basically, we want a way to track our memory allocations throughout the system, as well as the ability to use custom memory allocators for certain types of allocations throughout the engine. One of the things that we want to avoid is doing a lot of dynamic allocation on the fly. And so having a memory subsystem sort of allows us to control how those allocations actually occur. And the other thing that would be nice to have is a way to track how much memory is being used by what types of allocations we have. So how much memory we're using to allocate strings or textures, for example, we'll say arrays, dictionaries, all these things that we're eventually going to be creating. And so we need some way to sort of track that so that if we do wind up with perhaps a memory leak, this is one way that we could use to detect it. We could also use this as some very basic level instrumentation. And so having that control over memory is really the reason why we want to go ahead and set this up. And the system is actually going to be pretty simple on the surface, and all the complexities will be abstracted away. And as we expand this system, we'll make it more robust and add stuff to it as we go. But for right now, we're actually going to start off pretty simple. So to get started, the very first thing I'm going to do is within core, I'm going to create a new file, and I'm going to call that kmemory.h. And this is going to be the file that we perform all of our allocations in the system with going forward. So obviously, as with most of our other header files, we will do a pragma once and include defines h. And then, as I mentioned before, we're going to have a way to tag our memory allocations. So we will need a enumeration of what those memory tags should be. And I've gone ahead and pre-populated some tags here that I think we're going to need in the future, and obviously we'll be adding to this list as we continue. But the important things to note here is that we have an unknown type, which is sort of the default, right? So if we don't pass anything to our allocation routines that we're going to be writing here in a minute, it will be sort of filed away under the unknown category, if you will. And we're actually going to have logic to detect that, to say, hey, if you're using this, you shouldn't be. You should really be using a category for it. We also have all these other sort of categories in here. And then we have just a max tags here so that we can use that to iterate through all of these when we go to actually report on them. So this guy here will always be the last entry in this list. As with most subsystems, we will actually need an initialization routine, which will actually perform some basic operations and set up some stuff that we're going to need for this tagging stuff here. And so we'll have a initialize memory, and of course a shutdown memory. And of course these will not be exported because we're only going to be calling these internally within the engine. All right, so as you may have guessed, we are going to need a few interface functions to actually handle our allocations. And these are the ones we're going to need right now. We're obviously going to be adding to these as time continues, but we have a kallocate, kfree, k0 memory, kcopy memory, kset memory. So these may look familiar to you from the platform layer, and I did mention before that we do not want to be calling the platform layer outside the engine. However, these will all be exported. So these can actually be called from user code if we need to actually perform an allocation. But it allows us to control at the engine level how those allocations happen. So for example, we have our kallocate here, which takes in a size, this is basically like calling malloc almost. So it takes a size and returns a void pointer, but it also requires a memory tag. So you'd be passing it one of these things. This is how we're going to categorize our memory allocations. So for free, we actually pass the block, and we also pass the size here, which is not something that you pass to the normal free function, but we do it here because we're actually going to be tagging our allocations and keeping track of how big those things are. And so generally speaking, whenever we do an allocation, we'll know at some point how large that actually is, and we'll be tracking that somewhere. So when we go to free, it makes sense that we'd also have that information. And so what this basically does is it allows us to report on when we perform an allocation against a specific tag and when we free against a specific tag, which is the last argument here. We also have some convenience methods here, just one for zero memory, which just takes the block and the size of memory to be zeroed out. Then we also have a copy memory, which works just the same as a standard memcopy. And then we also have a set memory, which is the equivalent of memset. And again, this is so that we don't have to include those headers throughout our file, and we have a little bit more fine-grained control about how these things work under the hood, which we're not going to utilize right now, but I want to get these in place so that later we don't have to change all of our code base. We can just change the things behind this interface and go from there. So there is one last thing that I want to add, and it is also an exported function, which is to get the memory usage string. And this is sort of a debug function that we're going to have in place. I'm not going to mark it as debug for now. I may decide to do that later, but this is basically going to print out some usage statistics to the console. So this is basically what our k-memory interface is going to look like in the system. So again, it's pretty straightforward and simple, and it might seem like just another layer, but I promise you guys, you will see the benefit of this later on down the road once we actually start controlling how our allocations work. This will allow us to have very fine-tuned control over how we allocate for specific categories. Okay, so that is kmemory.h. We will also need kmemory.c, and of course that includes kmemory.h. It is also going to include the logger, as well as platform H, because it is going to be calling our platform memory functions. Speaking of which, before I go any further on this, I'm actually going to go to the platform H file, and if you recall, we actually had this platform allocate and platform free exported. We're going to not export those anymore, so I'll make that quick change. Jump back to kmemory.c. So the first thing that we're going to want is a very basic way to track our memory allocations. And since we are using an enumeration here, technically what we also have here is a set of array indices, right? Because it starts at 0 and then works its way up, right? So we can actually technically use this enumeration to hold all of our allocations, or at least the sizes of our allocations, within this particular category. So what I mean by that is back in memory.c, we're going to create a memory stats struct that's just private. And in that, we are going to hold our total allocated memory, as well as our tagged allocations. And you'll see here that I have the size of that array set to memory tag max tags. That way, whenever we add a new category here, we don't have to remember to come here and add this particular, we don't have to come and update the size of this. Okay, so now that we have our struct, we're actually going to create a static instance of that, just private to this C file. And we're just going to call that stats. And then after that, we're going to have our initialized memory, which simply zeroes that out. right? So it zeroes all of these counts out for us instead of having to do it manually. So the next thing that we need to set up is our kallocate method. And you'll note here that we take in a size and a memory tag and return a void pointer. So the very first thing that we want to do is we want to check this tag and say if that tag is unknown, we want to throw a warning about it saying, hey, you're using memory tag unknown, which is technically valid, but it really should be reclassed. So anytime we actually use this, we will get a warning about it. And we have that set up so that if we're just trying some experimental code or something where we don't want to create a class for it, we can put this in there and it makes it very easy to find. So first and foremost, we will define that. And then the next thing that we're actually going to do is we are going to update this stats, right? So the first thing we'll do in here is we'll say the total allocated, we're going to add the size that's passed into that. So that's the size in bytes, right? And then the next thing we're going to do is we are going to update our tagged allocations using the tag as the index into the array. We're going to increase the size of that by the size that's passed in. So this is how we're going to actually track how much memory we're using per category. So the next thing we're going to do is we are going to call platform allocate. We are going to pass the size, and we're going to pass false right now for memory alignment. I know that I've said I'm going to come back to that, and I promise we will touch on memory alignment at some point, but for now I'm just going to hard code that to false, and that's going to create our block of memory for us. And then the next thing that we're going to do is something that a typical malloc does not do for us. And we are actually going to zero out that memory. So we're going to zero out the block of memory for the size that it is. That way, any memory that we actually get from this will automatically be zeroed out. We don't have to worry about rubbish data. We will always get zeroed out memory. And then from there, we will simply return the block. So here, obviously, we want to do some detection on memory alignment. So I'm actually going to put a to-do to come back and revisit memory alignment. Okay? All right, so the next thing we have to fill out is our k-free, which is going to work almost like the opposite of this particular function, right? So the very first thing that we're going to do is, since we have this check here on allocation, we're going to have this check here on free as well. So if we're freeing with an unknown tag, we're actually going to warn about it as well. Okay, the next thing, as we have done up here, I'm actually just going to copy this, and instead of adding to the total size and tagged allocation, we are going to subtract from the total size and the tag allocation for that particular tag. Finally, we're going to call platform free, and again we're just going to pass the block and false for alignment. So I'm actually going to put a to-do in here to handle memory alignment at a later time. So basically, what we're going to be able to do is, based on the tag, we will be able to align or not align memory. Based on that is what we eventually want to go for, but we don't have memory alignment set up, so I'm not going to use it right now. Again, memory alignment is something I'll touch on later down the road once we actually need that optimization. But this will allow us to basically flip that switch from this point, and then anywhere in the system that actually should be using that will automatically get it when we make that update. Okay, so the next ones are pretty simple. I'm not going to go through these line by line because they're actually pretty straightforward. So we have k0 memory, which calls platform 0 memory, pretty straightforward stuff. Copy memory calls platform copy memory. K-set memory calls platform set memory. So again, we may need more fine-grained control over the way that these things work at some point. So we want that flexibility, but for now we're just going to treat them as a pass-through. Okay, one more thing that I want to touch on really quickly is we have our initialized memory. We also need our shutdown memory, which for now is actually not going to do anything because we don't have any allocations here to clean up, but at some point we may actually need to perform some cleanup, so I want to put the entry point here so that we don't have to change any of the outlying code afterwards. Okay, so we have everything here implemented except for our get memory usage string. So I'm going to go ahead and implement that now. And what this is going to do for us is it's going to print out a series of sizes for each particular category, basically telling us how much memory each category is actually occupying. But we don't necessarily want to write out some huge number in bytes, like something that looks like that. Obviously that's a crazy amount of bytes, but that's not really readable. It's not really usable. So we want some way to sort of translate to kilobytes, if we're in kilobytes, if we have kilobytes worth of memory allocated, or megabytes, or even gigabytes, right? And so what I'm going to do is some quick multipliers here. One for gigabytes, which is technically the measurement that we're going to be using, since we're using 1024 and not 1000. Megabytes and then kilobytes. And the difference between these, if you're not aware of that, is kilobytes and megabytes and gigabytes are measured by multiples of 1000. And what a computer actually uses is multiples of 1024. So technically this is the more accurate measurement to use. It's just gigabytes and megabytes and kilobytes are a little bit easier for people to understand on the surface, which is why those are the ones that are commonly used. But in this case, we're actually going to use the more technically correct measurement. So the next thing we want to do is we want a simple character buffer that we are going to sort of format some strings to, right? So I'm going to create a buffer with 8,000 characters. That should be more than enough. And I'm going to simply start that off with system memory use and then tagged, and snip in a new line here. We're going to essentially iterate through each one of the categories and print out on a new line how much memory that category is actually taking. So we have this first line here, and then we're basically going to append to the string as we go. So the very first thing that we're going to want is we are going to want to get the offset, and we're going to have to maintain this as we go. And the offset is basically the size of this string as it is now. So we're just saying the string length of buffer, which I don't think, we haven't imported that yet. So let's go ahead and include string.h. And just a hint as to something else that's coming down the road. We are eventually going to be replacing this with our own custom string library. So this is temporary. We will be writing our own with useful library functions and whatnot that will be helpful in processing strings. So I'll put a to-do there for that for now. All right, so the first thing we have is our offset. And what we're going to do is, as I said, we're going to loop through each one of these categories, or the tags, right? And we're going to print those out one by one, each on its own line. So the first thing we're going to do is create a couple quick variables. We're going to create a small character array here for the unit, and we're going to start this off with xib, which actually means nothing. The x is just a character that I've chosen, and we're actually going to switch out that x to something else depending on which one of these categories we fit. So that's sort of our template string, and this obviously includes a null terminator. That's why it's 4. And then we have our amount here, which we're defaulting to 1.0f, but our amount is actually going to be the calculated gigabits, megabits, or kilobits. So that needs to be floating point because it's going to be fractional numbers. So the next thing is some quick detection code here to see which category we fit in. So basically we check to see if this particular tag is greater than or equal to the size of a gigabyte. Then we go ahead and replace that with a G. So we replace the X with a G to make it gigabytes. And then we take our amount here and divide it by gigabytes to actually give us our final amount. We then do the same check. If it doesn't meet this criteria, we then check for megabytes and then kilobytes. And if it doesn't meet any of those, then it means that we just have an amount of bytes, in which case we actually just set the first character to B and then the second character to a null terminator, and that is what we put in instead. Okay, so the next step of this is actually going to be appending to our string. However, we have the size and the unit, right, to print out to the string, but we don't actually have a string representation of these tags. So what we're going to do for right now, and we will be making something that's a little bit more robust in the near future, But what I'm going to do right now is I'm going to create a array of character arrays, basically, and I'm going to call this memory tag strings, right? And this is going to be the same size as our tagged allocations, right? And we're going to have one of these string representations per category, and I've aligned these strings here so that they're all the same length. This is probably not the most ideal way to do it, but it is the simplest way. So for now, we're going to stick with this, and we'll come up with something a little bit more robust down the road. But what this is going to allow us to do is basically say, by index, get me the string for the particular category. One other thing we're going to need to do is at the top, we are going to also need to include stdio.h because we are going to be using snprintf. So back down here in our method, we need a line that looks something like this. So we're going to call smprintf, and we're going to say the buffer plus the current offset. So basically this is some pointer arithmetic here to say we want to start at the buffer plus whatever the current string offset is. Our buffer size is 8,000, so we won't go over that. And then here's our format string. So what this is basically taking is I've spaced this over a little bit just so that it's sort of 2 spaces in from where this string begins. It makes it a little clearer in the logs. And then we're going to print out a string, which is going to be our memory tags at index I, which is going to be our current memory tag. And then a semicolon, and then we're going to do some formatting here for the size. So this %.2f is basically saying that we want 2 decimal places for our fractional representation of how big of one of these units it is, except for b. So we're basically saying we want to format that down to 2 decimal places of our float, and then we're going to print another string after that, which is the unit, right? So memory tag string amount unit. From that, we will be returned a length. So smprintf actually returns the number of characters written to the particular string area that we've designated here. And so that is actually exactly what we need to add to our offset. So we extract that length, which is basically the number of characters written, and then we go ahead and we add that to our offset. I could have done this in one line, but I feel like this is a little bit clearer as to what's going on. So this is actually expecting to return a character array. And what we have here is basically a sort of a character array in the stack, right? This is not dynamically allocated. And so we actually need to return a dynamically allocated array, which is not ideal, but this is, again, something that's a debug function. It's not something that should be called constantly, so I'm not really worried about performance here. So in this case, I think it's fine to go ahead and return a character array. So what I'm going to do is I'm going to call the underscore string duplicate method, which takes the buffer string that we have here and performs a string copy to a new newly allocated pointer. So this actually performs the allocation under the hood and then returns that for us. And so we're going to assign that to something called outString, and then we're going to go ahead and return outString. So one thing we'll have to be careful with is anytime we call this, we'll also have to free that. Not ideal, but again, this is just a sort of debug thing for visualization. So this will never actually be used in a release build, so I'm not really worried about it from a performance perspective. Okay, so that pretty much takes care of memory for now. I think what I'll go ahead and do is go ahead and tie this into the application. So I'm going to actually put this is probably going to be the one subsystem that I'm actually going to include in entry.h. Because this is low level enough that I feel like it's actually needed at this level. So before we do anything else in our main function, we're actually going to include kmemory. And before we do anything else, we are going to call initialize memory here. And by proxy, right before we return, we are going to call shutdown memory here. So like I said, this is probably the only subsystem that's actually going to be created at this low level because it's so necessary to actually have this in place, because we're going to be doing lots of allocations probably at this level before we actually even get into the engine. So with that, I do want to point out something that somebody brought up in the comments, where the application calls initialize logging here in application create. And somebody pointed out that there are actual logs that are being written before this is called, which means that it will not be written out properly to a file when we actually start writing out to a file, which is fine because the only things that are actually called at that point are things which we don't necessarily need written to a file. So if that ever changes, I could just move this to entry.h as well and call it here. For now, I'm not going to do that. I'm going to leave it in application, but if for some reason we wanted to do that, we would do that probably right after initialize memory. So nothing should be called before or after these memory calls here, but if we wanted to address that, we could certainly do it that way. Okay, so one more thing. What I'm going to do is just to test and make sure that this works, I am going to do a quick search in our code for platform allocate. And you can see here we're using it in a few different places. So the platform the platform itself using it makes sense. Platform H, platform Linux. Okay, so these are fine. The only one that really doesn't make sense is this entry.c in our game. So let's go ahead and change this to, instead of using platform, we'll say core kmemory.h. And we'll change this to kallocate. And this, instead of wanting to know whether or not we're going to be aligning this or not, it wants to know what the memory tag is. So I'm going to say memory tag, and we'll use game for this, right? Because it is the game level. It makes sense to tag that allocation as the game. So if we go ahead and go back to our application, right before we begin our game loop, let's go ahead and call our method to actually print that out. So I'm going to include at the top here core kmemory. Okay, so right here we'll go ahead and just say kinfo and then get memory usage string, and we'll just log that directly. And I'm not going to worry about the fact that this is technically leaking memory. I'm only calling it once. I'm not going to worry about it. This is just a test to make sure this works anyways. Okay, so it looks like we have a couple of unresolved external symbols, initialize memory, in function main. Okay, so because I'm getting undefined or unresolved external symbols, I'm going to go ahead and export these for now. It's not ideal, but I can go ahead and move those later. So just so that it builds for us and that we can run it and test this out, I'm going to go ahead and do that. Okay, so I'm going to go ahead and run. And we now see that our log actually works, right? So we have an output for each one of these individual categories, right? And we're not actually allocating anything yet, but we do see here that our game does in fact occupy 4 bytes. So we know at least that this system is working as intended. Again, this is probably something that if we're really wanting to trace something down, we'd probably want to write this a few times, more than once, and at that point we'd probably want to manage the memory a little bit better. But for now, I think this is proof of concept that our system is working just fine. Okay, so one last thing I want to do is I want to just do a quick search for any mallocs that we're using to try and get rid of those things. And it doesn't look like we're actually using any that I'm too concerned about replacing. So I know that one of you had pointed out in a previous video that the platform layers are actually calling malloc. At this level, that is actually fine. I could change this to use the platform allocation, but this standard malloc at this level is I'm actually fine with, because at this point the only thing that we're actually allocating memory for is something that's part of the startup routine, in which case dynamic allocation is just fine. So I'm not going to worry about replacing these. Let me do a quick check also on free. And it does look like the only thing that is using free is, again, the platform layer, which I'm fine with. So I think at this point, that pretty much covers our memory system, at least for now. Now, I realize this doesn't look like we're actually doing a whole heck of a lot, but we're going to be tying in a lot of instrumentation to this, as well as custom allocation routines for some of these specifically that use custom allocators that we're going to be writing down the road. The other reason I wanted to put this into place, as I said, is because we don't want to have to go changing the rest of the application to use this down the road. We want to get this in before the application actually gets too large. That way we can just use this going forward. So there are a couple more small systems like this that we're going to be putting into place before we actually move on to the renderer, just because we don't want to have to go back and do tons of refactoring later. So that is going to do it for this particular video. Thank you guys so much for watching. Please give the video a thumbs up if you liked the video. If you haven't already, consider subscribing. Hit the little bell notification there so you get a notification as to when the next video in this or other series drops. And if there's anything that you guys have seen along the way, leave a comment in the comment section below and I'd be more than happy to answer it. Thank you guys so much. I hope you learned, and I will see you next time.